So can we start?
Yes, Pragati. Just a minute. Okay, welcome you all again. In this session, this hands-on session on the GPU computing using CUDA. Okay, we'll see some of the programs. I will show you how to run the program on a Google Colab and some other basic informations as well. Okay, so okay, so what happened in last session? In last session, we have seen if you want to execute a program on a GPU, so what we need to do, we have to write a kernel code. Kernel code which is going to execute in each CUDA thread. Okay, and these threads will be assigned to the GPU core. For that purpose, we have seen that we know about how the internally CUDA understand the hardware of GPU, where we have multiple streaming multiprocessor. Each streaming multiprocessor is having multiple processing core inside it. Very much similar to that, we have seen that if you want to create like 1,000 threads, those threads are arranged inside the block and blocks are arranged inside the grid. Okay, so for the threads, we have made a logical arrangement. Now, if we want to execute a CUDA kernel, and that kernel should be executed on each thread, whatever threads we have defined. So how that's going to happen? How that's going to happen? That's going to happen with the help of CUDA SIMT architecture. That is called the CUDA single instruction multiple thread architecture. That is called the CUDA single instruction multiple thread architecture. So how this, let me tell you about how this CUDA SIMT architecture works. So you know about the hardware architecture of the GPU, you know about the logical arrangement of threads. Now, for the execution purpose, this complete a grid of thread will be assigned to a GPU. Okay, a grid of thread will be assigned to a GPU. After that, what will happen? That grid is having multiple blocks inside it. A block will be assigned to a streaming multiprocessor. Okay, so from inside the grid, a block will be assigned to a streaming multiprocessor. And like if your machine is having 10 streaming multiprocessor and you have created 20 blocks, so one block will or two blocks will be assigned to one streaming multiprocessor. Okay, so block of thread will be assigned to a streaming multiprocessor, and the multiple blocks can be assigned to a thread. So now what will happen? Now the actual execution will take place. Now the multiprocessor is responsible to create, manage, and schedule the execution of threads. Every multiprocessor is responsible for managing and scheduling the execution of threads. For that purpose, what that multiprocessor is going to do, like you have assigned a block of threads to multiprocessor. If that block of thread is having 100 thread inside it, what the multiprocessor is going to do, multiprocessor will divide it into group of 32 threads. Okay, a block is having 100 threads. What the multiprocessor is going to do, multiprocessor will divide into the group of 32 threads, and this group of 32 threads is called warp. Okay, this is called warp. Thread of a block are divided into group of 32 threads called warp. And now finally, this one warp will be assigned to the cores of multiprocessor. Okay, we already know that one multiprocessor contains 32 cores. So one warp is also having 32 cores, 32 threads. So now one warp will be scheduled for the execution on these core of streaming multiprocessor. One thread will be assigned to one core. So what is happening? If our block was having 100 thread, it means four different warp will be created. One warp will be selected at a time, and threads of one warp will be assigned to the processor of streaming multiprocessor for execution. So these 32 threads out of 100, 32 threads will execute parallelly, and the same thing will happen in every multiprocessor. In every multiprocessor, same thing will happen. So what the multiprocessor is going to do? Multiprocessor will pick up one warp and assign core for the execution. Now, when one instruction will be executed for one warp, it will remove it from the core, and next warp will be assigned to the core. Okay, and in this way, all the threads inside a block will be assigned to the core for execution. Okay, so in this way, what is happening, you can say that all the threads of a warp execute parallel. And internally, how the execution will take place? You have instruction unit inside your streaming multiprocessor. Instruction unit, that multiprocessor will schedule one word for the execution in the processors, and then one instruction will be issued from the instruction unit, and that instruction will be executed by all the threads. that's called the that's called the SIMT architecture, single instruction multiple thread. A single instruction from the instruction unit will be issued, and that instruction will be executed by all the 32 threads which are assigned to the core of a streaming multiprocessor. And these 32 threads in one multiprocessor are going to execute parallelly, and the same thing is happening in other multiprocessors as well. After execution of one instruction by a thread of warp, what will happen? The next warp will be scheduled for the execution. So in this way, all the threads inside a block will execute. It seems just like all of them are executing parallelly. And this is called the SIMT architecture, single instruction multiple thread. So in this way, in GPU, internally parallel execution take place. So the important thing over here is, like, if all the 32 threads which are executing inside the core of a streaming multiprocessor, if all of them are going to execute the same instruction, it's good. If suppose you have defined a if instruction over there, and that if instruction is true for only 10 threads and wrong for all remaining threads, then what will happen? Those 10 threads will go inside to the if condition. They will execute their if condition during the next iteration when they will be scheduled for the execution. But the remaining thread during that time will be in ideal situation, ideal. So you will not able to get the actual parallelism over there. Okay, so one thing which we have to keep it in the mind, we have to to try to write a code which should have minimum number of conditional operation, so that will be more efficient for us. And one more thing, like what we have done in our example, when we have created 100 threads inside a block, and now what is happening, how the warps are created. One warp is having 32 threads. For a block of 100 thread, four warps will be created, three of 32, 32, 32, and the fourth warp is just going to have four threads. So when the fourth warp will be assigned to the streaming multiprocessor for the execution, only 4 core will be used. Remaining 28 core will be idle. So that's the distribution of block inside distribution of thread inside a block is also not very efficient. So how we can make it more efficient? Always keep it in mind that the number of threads inside a block should be in multiple of 32. Keep it in a multiple of 32, then it will be good. Your program will be more efficient. Like we are talking about the parallel computing, and ultimate goal is speed up, get some kind of speed up, do the fast computation. So we have to save every cycle, and for that purpose, what's a good idea? The number of thread inside a block should be on multiplication of 32 threads. Okay, so that will be good. Like if we have created a block of somewhere, um, like in our case we have created 100 thread, and in place of that, if you have created 128 threads inside a block, that will be the better idea, in place of creating 100 threads inside a one block. Now the thing is over here that one streaming multiprocessor can be assigned multiple block. When the multiple blocks are assigned to one streaming multiprocessor, what will happen? All the warp of these multiple streaming multiprocessor will execute parallelly. Okay, when the scheduler will try to find out which is the next warp which need to be scheduled for the execution, it can pick up any one of them, all the warp. Like if you have assigned two blocks to one streaming multiprocessor, we will have 8 warp over there. So the scheduler will pick up any one from these eight warps. Okay, so all the threads of blocks which are assigned to the same streaming multiprocessor will execute parallelly. And one more thing over here is you can synchronize the thread inside a block. Only all the threads which are present inside one block can be synchronized. They can be synchronized at a particular point. Synchronized means, suppose one thread have completed its operation but remaining are still doing their job, so that the thread which has completed its job, it should wait for others to complete their job, and after from that point onward, all of them are going to execute simultaneously. So the important thing is that the threads inside a block can be synchronized. This is all those things are a part of CUDA SIMT architecture. Okay, single instruction, multiple threads. I have taken an example over here. Like we have created like a multi-threaded program. We have created 8 blocks. 8 blocks. Suppose our GPU is having just 2 SMs. So what will happen? 4 blocks are assigned to the SM number 0, and 4 blocks are assigned to SM number 1. Similarly, if our GPU is having four streaming multiprocessor, if it is having more number of streaming multiprocessor inside it, so what we can do? 2 blocks will be assigned to one streaming multiprocessor. Okay, so if our GPU is having more number of streaming multiprocessor, as we know, if more core will be available, you will get more performance, more speed up. Okay, this is also a block diagram. This block diagram or this image is showing. We have, this is a complete grid of below this box. Complete box is a grid of threads. Internally we have multiple block 1, block 2, and then this block n. And here a block of thread is having multiple thread inside it. So what will happen? All the thread present inside a block will be divided into a warp. This is the warp 1. One warp will have 32 threads, and remaining thread will be present in other warp. Now one warp will be assigned to processors of core of one streaming multiprocessor for execution, and one instruction will be issued from the instruction unit of streaming multiprocessor, and all these threads will execute the same instruction at the same time, and this will happen in all streaming multiprocessor parallelly. So that's the way the parallelism is achieved in a CUDA program. Okay, this way the CUDA program uses the GPU architecture to achieve the parallelism. It's not like that you have 500 core and you have created 1,000 threads, so you will directly assign 500 threads and then the 500 threads to those core. There is some internal arrangement of the logical arrangement of threads and logical arrangements of and physical arrangements of GPU cores, and we have to match that arrangements. That only then after we are going to get the best performance for our problem. Now let's see one example. I have taken the example of the vector addition in the last session as well. Let's see if we want to write the complete CUDA program for that vector addition, then how it will be, look like. Okay, like this. This is the CUDA code. Okay, this is the CUDA code. Is this properly visible to you guys? Abba, is this code? These codes are visible, or I need to increase the size, font size?
So, it's visible to me, sir, but if the participants are finding it good or if they're finding it difficult, so depending on that.
Okay, if it's visible good to you, then maybe it will be fine. I hope. Okay.
Okay.
So I have written this CUDA program in a notepad. I will try to run it. Don't go with the header files. Don't care for the header files. We will see the header files when we will uh, trying to execute that code. Generally, the CUDA programs will have the header file CUDA runtime.h, device launch parameter.h, and some others are C programming header files, studio.h, time.h. Okay, the C programming header files. Okay, very much similar to the C program. Like, it's come over here. This is the host code, the most important. Very much similar, like when we write the C program or C++ program. This program is very much similar to that program. Okay, so what we are doing over here, inside the main function, we have defined a variable of size 90 lakhs. Okay, 90 lakhs element over there. Then this is we have defined a variable size of type size t, which is available in the C programming. Size t to use to define the size. So what will be the size of that? N into the size of integer. Okay, then I have defined two variables for the clock to measure the time. We'll talk about that in actual program when it will run. Okay, so the clock t is also available in the C programming libraries. So we have defined two variables, start and stop over here. Then now we have defined three vectors. Okay, dynamic memory allocation with the help of dynamic memory allocation, and how much memory is allocated. Memory is allocated of size. Okay, and size is actually n into size of integer. So dynamically that amount of memory will be allocated and address will be stored into is h underscore a. It means host underscore a, array in a host side, array a in a host side, array b in a host side, and this is the array c in a host side. We have defined three array, h underscore a, h underscore b, h underscore c, and we have allocated memory, uh, dynamic memory allocation through the malloc function for those three arrays. Now a very simple line to code, to just we are putting some values to those vectors. We are initializing those vectors. So for the initialization, what I did just for the array a, every element is having value I into 2, nothing else. And array b is having value j into 5. Every element is having element position into 5. That was the value stored over there. Now, this is the data which is currently available in our CPU side. And I told you, if you want to execute if you want to execute your code, parallel code on a GPU, if it is using some data, that data should be available on the GPU memory. So what we need to do, we have to copy that data to the GPU memory. But before that, we have to define um, we have to allocate memory for that data as well on a GPU side. So for that, we have a function called CUDA malloc. CUDA malloc. Okay, this is the way what we have done. We have defined a pointer device array A, device vector A memory for inside the device, and how much memory is allocated of size. And for that purpose, like malloc is available for the CPU side, CUDA malloc is available for allocating the memory in a GPU. So for that function, we use the CUDA malloc, and then the void, return type void, and address will be cached by d underscore a. Now similarly, we have allocated the memory for array B and allocated the memory for the array C. Okay, we have created three arrays for the CPU side, and for the same amount of memory we have reserved in a GPU side as well. For the GPU memory allocation, we have to use the CUDA malloc function. CUDA malloc function. Now, the data, initially what we have done, we have created the data in a CPU side, memory is allocated, and the data is initialized. Array A and array B are initialized. So data is currently present on our CPU memory. So what we are, if we want to work on that data, if we want to perform the addition of that data on a GPU side, we have to copy that data from host to device memory. Host means our CPU, and device means device is over here is the GPU. For that purpose, what we need to do, we have to copy the data. For that, we have this CUDA function, CUDA mem copy. It's actually CUDA memory copy, short form of that. So it is used for copy the data from CPU to GPU, copy the data from GPU to CPU. So here what we are doing, we are copying the data from CPU memory to GPU memory. That's why. So what we are doing, we are copying the data to the device memory. From where? From host memory. Host is CPU. How much data we are copying? Of size. And what is the direction of data copy? Copy is host to device. This is the flag which we have to write over here. CUDA memory copy host to device. So here we have host A vector is copied to the device A vector. Now it's very similar to that. CUDA memory for the host B to device B. Host B data is copied to the device B, and how much data of size, and the flag is host to device. So data is copied from host side to device memory. It means we have copied the data from the CPU memory to GPU memory, and after that, now data is available. Now we have to see how many threads we want to create, and what will be the thread arrangement. So here what we have done, we have created two variable, threads per block. How many threads will be present inside one block? Blocks per grid. It means how many blocks will be present inside a grid. Okay, so here I have initialized threads per block is equal to 1024. I want 1024 number of thread inside one block. This is one dimensional thread arrangement. We are talking about one dimensional thread arrangement inside the block. Okay, so this will be one dimensional thread arrangement. Now we have 1024 threads in one block. So how many such blocks are required inside one grid? That could be evaluated with the help of like this simple instruction, simple statement. Blocks per grid, n plus n is the number of element we were having, okay, plus threads per block. Here what is the aim? Here we have ultimate aim is that we have to create we have to create as many number of thread, so that every thread need to work on only one data item. So n number of data items are available with us. So minimum n number of threads we want to create. Minimum n number of threads we want to create. That's why I have written this, like 104 threads have been present in one block. And so how many blocks will be present inside one grid? That will be evaluated with the help of this. N plus thread per block minus 1 divided by thread per block. You will get how many blocks will be present inside one grid. Okay. So we have got the logical number of threads. How many threads are present inside a block and how many blocks are present inside the grid. Now the next thing come in a picture. That is actually function call. This is the vector addition. This is the vector addition kernel function I have written above. I will talk about that. So this is the vector addition function. This is the way of calling. This is the function call. This is the function call. Which function we are calling? Vector addition. Vector addition, or you can solve the kernel function call. Vector addition kernel function has been called. These are the parameter which has been passed. What are the parameter? Device underscore a, array a, device array b, device array c, and n is the total number of elements inside the array. Okay, these are the parameters which we are passing to that kernel function. And other than that, inside this triple arrow in both side, what we have written over there, blocks per grid, comma, threads per block. This is the thing which we are telling to the CUDA compiler, how many threads we are creating, and what will be the logical arrangement of those threads. Okay, how many threads we are creating and what will be the logical thread arrangement will be there. The CUDA compute engine will identify that thing with the help of this information. How it will identify? Threads per block, it means how many threads will be present inside one block and how many such blocks are there in a grid, block per grid. On the basis of that, by using these two values, the CUDA compute engine will create the threads, required number of threads, and call the function vector addition, kernel function vector addition. Every thread will execute the same vector addition function. Vector addition function. And what is that vector addition function? Is very simple function. This is the vector addition function. What is the way of writing the function? Kernel function will execute on the device side. That's why they have written device code. How we write it? Underscore underscore global underscore underscore. This is the thing which we have to add, and the remaining thing is very much similar to the normal function, normal C function. Void is the return type, and then the vector addition, new vector addition, the name of the function, and then the parameter, pointer a, pointer b, pointer c, and the n. Now this thing which I have already explained you guys, this line will calculate one index. Like, now what is happening? This function is, kernel function is executing inside every thread of a grid. So how the thread will identify on which particular data item I have to work. So how it is going to identify? It will calculate an index value. And how that index value will be calculated? Inside the thread, every thread is having a unique thread ID. So that value will be gone. That value will be found with the help of thread ID x.x built in. Okay. Now block dimension, how many blocks are, how many threads are present inside one block, and then what is the block ID? By using that, in the last session I have told you how to evaluate this index value. So every thread will evaluate this index value. After evaluating the index value, the thread will identify, okay, on which particular data item I have to work. And the statement, this statement, it's not necessary to check, but sometimes you can write it like it's checking if n is I is less than n, then what we are doing? Okay, C of I is equal to A of I plus B of I. C of I. So for every thread, this I value will be different. So every thread is going to perform the addition on different location of A and different location of B. So A of I plus B of I will be added and stored in the C of I. But every thread will be working on a different location of the array. So this addition, logically, this addition will be performed parallel. Okay, so this CUDA kernel will be executed parallelly on all the threads which we have created. And how many threads compute engine will CUDA compute engine will create? It will create according to the way you have defined it. Number of threads per block you have defined, the block per grid you have, the way you have defined. By using that information, it will be it will create the threads and execute the kernel function inside every thread. Now, after the completion of the execution of every thread, what we need to do? Okay, data is now present on a GPU memory. You cannot access it. This the normal IO operation, it means display it on the screen. You cannot see it. You cannot display the data which is present on a GPU memory. If you want to check it, if you want to see it, what is the data present on the GPU memory side, you have to copy back it to from GPU memory to CPU memory. Okay, you cannot write the print instruction inside your kernel function. That kernel function is going to get executed on the GPU processor, and the GPU processor was not managing the this IO operation, input output operation, all those things. Okay, so keep it in mind. You don't need to write printf, scanf, all those things. If you want to do something like printf, scanf, you have to copy back data from GPU memory to CPU memory. So this is the same instruction I have used again. Same function, CUDA memory copy, and this time what we are doing, we are copying the data. Device array C is copied into the host array C. And how much data will be copied? Of size. And the flag is here, CUDA memory copy from where? Device to host. This time the data copy will be from device memory to host memory. Okay, and important thing is that whenever you define, if we want to find how much time this execution take place, so we have to consider all these things as well. All these things as well, it means how many the time which we have taken to copy the data from CPU memory to GPU memory, and the time we have taken to copy the data from the GPU memory to CPU memory. That's why these two clock variables, I have started the clock over here, started counting the clock from this point and stop it here. This is between these two clocks, all the statements which are required to perform the GPU operation. Now, if you want to find how much time that operation has taken, that there is a function print elapsed time, and we have passed the start and stop. I hope you guys know about that, what it do. It's a time function. It's whenever we have written like this, start is equal to clock, we have called the clock function. Clock will return whenever we start the execution of a program, clock start, and how many cycles completed up to this point, that count will be stored in a start. Then when we have written stop is equal to clock, so how many cycles completed up to this point, that will be stored inside the stop. So stop will always, the value of number of cycles completed up to the second point will always be more than the first point, and on the basis of that we will calculate how much time this calculation has taken place. So stop minus stop, this is the stop minus start divided by clock per second, and this will give us the elapsed time in a second, how many seconds this execution has taken. Okay. So this is the simple time calculation. There's nothing to do with the CUDA, but you will able to find out that. Okay. So that's the simple CUDA program. Here what I have done, uh, these are the instruction like CUDA free. Always when you write a CUDA program, after writing that, whatever after the execution in the last statement you should write free the memories, device memory, and also the data which is allocated in a host ke liye you have, for the host you have the function free function, and for the CUDA side to free the memory use the CUDA free, very much similar to the free function. Okay, it's going to do the same thing which free function is doing in C programming. So your data will be free. So this is the CUDA program, which is actually what it is doing. It is performing the parallel addition, element-wise addition of two vectors A and B, and storing that output in a vector C. So for that purpose, what we have done over here, we have created two arrays in a CPU side, then initialize those two array. Finally, we have created two arrays on a GPU memory, copy the data from CPU to GPU side, call the kernel function. Before calling the kernel function, define how many threads you want to create and what will be the thread arrangement. And after the completion of the kernel execution, copy the data from CPU side, GPU side to CPU side, and now you can check um, your answers. It has completed the operation successfully or not. And the final thing is that after the execution, we have to free the memory. And how we are going to free that memory? Use the CUDA free for freeing the memory on the GPU side, and free function to free the memory on a CPU side. Okay, so this is the simple CUDA program to perform the vector addition, the simplest program, and most of the time that's, it's like hello world for the um, CUDA. Okay. Now let me show you how to run this program on a. Just wait a minute. I hope you guys know about the Google Colab. So actually, Google Colab is a free Jupyter notebook environment that run entirely on a cloud. Okay, so Google has provided that services to you. You can write your code in a Jupyter notebook. uh, Actually, uh, it's like it will provide you a platform where you can create your environment and run your code. Okay, whatever data, whatever program you are writing in a Google Colab, it will be saved on your Google Drive. Okay, and sometime like some of the databases, freely available database like the Kaggle database, you can directly import the data from the Kaggle database to the Google Colab. Okay, and the good thing for us over here is that Google Colab is providing the free GPU to us. I don't have the GPU with my laptop, and I currently am present in a remote location, so I cannot access all the GPUs which are available on our college system. So currently we have really good GPUs with us in our college system, at least in a data centers. So I cannot access them, but at least we can feel, or we can see how to run the CUDA program on a Google Colab. So yesterday I have run one, I have created one notebook over here. So what you need to do, you just need to open a notebook like I have studied on CUDA 1. So this is the already existing notebook. Let me Abha, my screen is visible to you? You guys, screen is properly visible now. Are you able to see what I'm doing over here?
Yes, sir.
Yes, sir.
Okay, that's fine. So in Google Colab, what we need to do, we have to create a new notebook. Create a new notebook.
Hello, excuse me, sir. Audio is not clear, sir.
Audio is not clear.
Sir, it is clear actually.
Okay, please check it your side because I think in my side, internet is good and audio and video is working properly.
I
Yes.
can hear the audio and see the good video.
Okay, now. Okay, that's fine. So what we need to do, I have opened a new Jupyter notebook in a Google Colab. Just modify the name, whatever you want to be. Like I have written it uh, two. Okay. So this is the CUDA 2, and if you want to run a GPU code, so important thing is that add a machine. So modify the notebook setting. In the notebook setting, add the hardware accelerator GPU, not the TPU. Just add the GPU, and save it. Okay, so you have an environment now available with you, with which is having a GPU, CPU as well as the GPU with you. Now what we need to do, I have got some instructions from the GitHub. How what are the things which we need to do to make a setup for execution of CUDA program in Google Colab. So I'm doing the same thing. Okay, now copy it over here. Remove these statements will remove if we have any setup over there, already existing setup for the CUDA inside my machine, inside my environment. So it will remove it. So I have just executed it. All these things will take some time. Okay, in the first cell. So thing is that whenever you are going to um, execute, if you will get log out from this environment and next time again log in, and if you want to execute your CUDA program, you have to run all those things again. Like, so a good idea is that just save your cells, Jupyter notebook cells over there in your machine. Okay, so like I'm running it over here. It will take some time. The next instruction, when I'm going to install the CUDA, it will take nearly 5 to 6 minutes. Okay, so that's done. That job is done. Now, after that, what we need to do, add the next Jupyter cell over here. We have added the next one. I have, okay. Now, these are the statement to, it will install the CUDA 9.2. Currently, the CUDA 11.5 or 11 CUDA version 11 is available with us, but I'm working on a CUDA 9.2. Just install it. So this will install the CUDA 9.2. Just wait a minute. Let me. So here in this these statements, I'm installing the CUDA environment, CUDA 9.2 in my Google Colab. Okay, this will take some time. It will take nearly 5 to 6 minutes. So just wait patiently, no issue. This step gonna take time because it's downloading the CUDA 9.2 from the NVIDIA sites and then installing it. Okay, now CUDA has been installed in our Google Colab setup. Now the next, let's add one more cell over here in this cell. Okay, just to check that CUDA has been properly installed. If you will run it, it will give you the CUDA compiler version. So CUDA compiler version 9.2 has been installed. Add one more here, installing some. Plugin for the Jupyter notebook so that it should be able to run NVCC compiler. Okay, NVCC plugin installed successfully. Now one more plugin will be there. Okay, so installation part has been done. Installation part has been done in our CUDA side. Let's try to write. Okay, this is the program which I have explained to you guys. Add one more cell. So this is the same program which I have explained to you guys. Okay, I'm getting a warning message that I'm not using the GPU. I have requested for the GPU and not using the GPU. Okay, so now whenever you write the CUDA program, first line should be this percentage CU over here in Jupyter notebook now. Okay, in like in normal, if you are using Visual Studio, you don't need to do all those things. You just need to add the header. You just need to save it like .cu. But here, in person CU and the header files, and after that the same program which I have explained to you guys now. Device code, vector addition, the elapsed time, host code, C, 9 lakh elements, same code. We will run it. Okay, it's completed in 0.034 seconds. And I have just print some of the values, first 100 values, to just check job has been performed properly or not. So these are the first 100 values are displayed over here. So this is the same program which I have explained to you guys. Define the variable n, initialize it in the size 9 lakhs, created a variable size of integer type. Okay, allocated memory for array A, array B, and array C on a host side. Then initialize both the array A and B on a host size. Device side, for the device, we have allocated memory on the device side. We use the function CUDA malloc. Then copy the data from host to device side. Okay, use the function CUDA memory copy. Then define how many threads I want to create, threads per block per grid, and then call the function vector addition function. After the completion of the vector addition function, copy back the data from GPU memory to CPU memory. And here I have closed the clock and calculated the how much time this operation has taken. Here I have displayed some values, and this is freeing the memory. Okay, so this is the simplest CUDA program which we can run. I have some other programs as well. Let me just show you. Okay, I got one program, a Bytonic sort, one of the one of the parallel bitonic sort, which is the fastest sorting algorithm available. Its implementation for the GPU, parallel implementation on a GPU. Okay, they have claimed, I got it in a paper, that they have claimed that that's the fastest sorting algorithm for the GPU based machine. Okay, it's bitonic sort, very much similar to the merge sort. And you guys know that the merge sort can execute parallel. So just wait a minute, let me open another editor. Open notebook. Okay, let me tell you one more program that will tell you some basic information, like this one. This is also a kind of hello world program. Uh, okay, this program tell us which GPU, like Tesla K80. Tesla K80 is the GPU which is available to, and the GPU number is 0. Like if your machine is having the multiple GPU, so every GPU is going to get a number, and the first device will get the 0, and then 1, 2, so like that. So the device number is 0 and its type is Tesla. Some other properties are also displayed: memory, clock rate, memory bus width, peak memory bandwidth, how much data copy rate is available over there. And it has done simple addition, just kind of hello world. So this is a function available, CUDA get device count, and CUDA get device property. Actually, it's a CUDA get device property function, and it will return all the properties of the device available to you. Okay, the CUDA device available to you. Not every, and even though every NVIDIA GPU is going to support the CUDA, you have to check that your GPU, your device is supporting the CUDA programming or not. If your system, if you are using the simple system, what you can do, there is one software, like I will talk about this GPU caps viewer. Use this GPU caps viewer. If you are using the Windows machine, just use this GPU caps viewer software. Install in GPU caps viewer. It will return all the properties of graphics card. So he gave it to me. Like you can see, it's a GeForce GTX 1050 graphics card. Okay, compute capability, which version of computation supports 6.1, memory clock, core clock, so every information. Warp size, what is the warp size? 32 is the warp size. How many threads can be present in one block? 1024, and these information can be different for different graphics card. Okay, so number of threads, maximum number of threads you can create, it depends on your graphics card as well. So you can check your machine if it's support the graphics, it supports the CUDA environment or not. You cannot just start the CUDA programming over there. You have to check your machine support. So that's why for the programming, with the help of program, you can check all those things as well. But some other softwares are also available with the help of which you can check your machine is supporting the CUDA environment or not. So like this one, I want to run one more program. Okay, this is the bitonic sort, parallel bitonic sort. This is I got it from somewhere on a GitHub, I think. Yes. So bitonic sort works. It's very much similar to the merge sort, and it's work only if the list of the data which are available, the count should be in to the power n terms. Okay. They have written a very efficient bitonic sorting algorithm. I've not checked all that steps how it's working, but I just so in their bitonic sort, the important thing is that they have already defined how many threads and blocks. So threads, it means the thread inside one block, and blocks means block inside one grid, and they're doing one dimensional arrangement. So they have defined it. They have defined it in their example, and if you want to modify it, you have to modify it over here. So what their program is doing, their program is generating using a random number generator to generate a list of that many numbers, like how many threads they are creating: 1024 threads per block. And how many blocks? 64,538. So if you can multiply these two, it means to the power 14 into to the power 9, it means near about to the power 23. This is the size of the list which they are trying to sort with the help of this example. To the power 20, to the power 23 elements are available over there. And how they are generating that those to the power 23 elements, they are using a random number generator. That random number generator is this random number generator is generating those to the power 23 different numbers. You can see, if you will run, it's really very efficient code. I've checked it, because I have one more code which was written by one of my student, but that is not that much efficient. Okay, you can see it took just 0.795 seconds to sort to the power 23 elements. Okay, let me try it for some other. To the power 25, it will make it to the power 25, no, 24, to the power 24, because blocks are now to the power 15. Something is wrong. Oh, upper was to power 14, then below was to power 15, but let's see it. I've just modified the size for some. Now this time, just take 0.879 second. Okay, so these are the parallel CUDA code they have written for the sorting operation, parallel sorting operation. Uh, we have written some code for the parallel graph operation, parallel case shortest path algorithm, parallel shortest path, all pair shortest path, but all those codes are not available with us current, so I cannot show you. But let me show you one more code. But I just want to tell you that what's the problem you will face if you have so many if and else condition in your program, like this program. You can see like this over here. Now you can see this is the kernel function, but how many if and else are having, and even if and else and sync thread we use to synchronize the threads. This sync thread function also reduce the performance. We have to use it as less as possible. Okay, if else condition, we have to minimize the if else condition in your program, and these sync thread operations. This is also a sorting. It's a matrix based sorting algorithm, sorted matrix. Okay, if you have a list of element available, array is available, what we are doing, array is represented in the form of a 2D matrix. Row wise row wise that matrix will be sorted, then the column wise matrix will be sorted, and after that in that sorted matrix we are trying to find out the correct position in sorted array, correct position of every element inside the sorted array. So that was the purpose of this program, that code. But that code is not performing well at present. It's not using the memories as well very efficiently. Something we have just run it. The main purpose of showing this code is to show you we have to minimize the if else conditions and sync thread statements in your program. You will minimize it, your program will be faster. Like you will see the result of this program. Okay, here it's failed. I have given some memory copy. What was the size? You can see the parallel version took 0.5 millisecond, the serial version took 0.3 millisecond. Data size is not also too large because the graphics card which is available with the Colab, it's also not that good. So it's up to you, but you can write your code, your own CUDA code, and you can execute it. But if you want to really perform the real-time execution of some parallel computing program, you should have your workstation with you, and you should have the latest graphics card with you. These are good to test your programs. Okay, just write it, test it. But if you want to see the real performance, you should have a latest graphics card with um, more number of cores available on it. Okay, so that's all from the Google Colab side. Okay, Google Colab side. Now move to the other thing. One more thing I want to tell you guys. I have shown you how to run the CUDA program. Okay, one important thing now available with the CUDA programming is called overlapping operation by the default stream. Okay, so there is one thing that is called the stream. Whatever GPU operation we have defined in our program now, copy the data from the CPU memory to GPU memory, copy the data from GPU memory to CPU memory, or call the kernel. These are called the CUDA operation. Okay, CUDA operation or device operation, GPU operation or device operation. Okay, so what happens if you have not defined any stream in your program? All these things come under the default stream. Okay, all these things come under the default stream. So what this statement said, all device operation, kernel and data transfer in CUDA run in a stream. When no stream is specified, the default stream is used. Like in our program, whatever example we have taken, we have not defined in our stream. If you will go for the really good example which are given in the CUDA library, you will find some of the programs are also having the CUDA stream. So if you are using the CUDA stream, then in that case, what we can do the overlapping between the data copy operation. You are copying the data from CPU to GPU in one stream, and in another stream you can perform the data copy from GPU to CPU. But in our example, we are not taking all those things. I'm just talking about the default stream. So what is the property of the default stream? In case of if the instructions are defined inside the default stream, like the example which we have taken, where we are doing the data copy from CPU to GPU, calling the kernel, and then finally copy the data from GPU memory to CPU memory, like the example which I'm showing over here. CUDA memory copy, and here we are doing some kind of memory copy from host to device, then calling a kernel increment function some function is there calling that kernel, and finally doing the data copy from host to device. All these all these device operations are going to run on a default stream. And what is the property of the default stream? No operation in a default stream will begin until all the previously issued operation in any stream on the device has completed. Okay, like if you are performing the CUDA memory copy, this CUDA memory copy will complete after the completion of this increment function will call. After the completion of this, CUDA memory copy function will be called. So this is happening in the default stream. But even though one thing is there, like what will happen when this CUDA mem copy, the first statement will execute, CUDA memory copy operation will complete, and after the completion of this operation, control will be transferred to the next instruction, like this kernel call. But what is the property of the kernel call? If you will call the kernel function, what the system will do, CUDA will call this kernel to the device side, and control will immediately transfer to the next statement. Even though this kernel function is executing on a GPU side, but control will be transferred in on the CPU. Control will be transferred to the next instruction, because all these device operations are defined inside the default stream. That's why this CUDA memory copy will not start, because until unless this kernel execution will be completed. But what is the important what is the advantage of that? Like what you can do, you can write a CPU function. Like here I have written in this example we have a my CPU function. So what will happen, the CUDA memory copy will execute it. Okay, after the execution of the first statement, control will be transferred to the increment kernel function, and increment kernel function will get called, and immediately control will be transferred to the next statement, even though this increment function is still executing on a GPU side. So what you can do at the same time, we can do, we can execute some function on a CPU as well. So in this way, CPU operation and the GPU operation will be overlapped. You will get more speed up. You can perform some kind of operation, like just hypothetical example, you have an array and you want to perform the one operation is like do the find the square root of every element of that array, and the second operation is perform some kind of addition of 2 in every element of that array. And after that, whatever output in we are going to get in both the operation, that will be added, something like that. You have to add both the output, something like. So here we have two independent operation. So one you can perform on a GPU side, and one you can perform on a CPU side, and both operation will be performed simultaneously. What is happening, maybe GPU will be slower, but even though that will be utilized. So that's the advantage of using the default stream. And in this way we will be able to parallelize the CPU and GPU operation as well. Not just the GPU is parallelly executing the code, CPU at the same time is going to execute some kind of operation. So that's one advantage of using the default stream. Okay. Now I have already talked about this. Not every GPU is going to support the CUDA programming. You have to check that it's supporting or not. So you can use this GPU caps viewer. GPU caps viewer is the software which is available for the Windows machine. You just install it and you can check it with the help of it. Your machine is supporting the CUDA or not. Okay. Now I'm just let me just tell you one more thing that is not available to me, but I have the document. Suppose if you want to run the GPU CUDA program in your machine, you can use the Visual Studio front end. You can visualize the Visual Studio front end, and for that purpose, you have to just install the Visual Studio, install the CUDA toolkit, download the CUDA toolkit from the NVIDIA sites, and some other CUDA software. It's not necessary, but this CUDA toolkit is very important. You have to because this CUDA toolkit is going to have the NVCC compiler, which is actually compile the CUDA code, whatever code you have written in a CUDA. So install the NVIDIA toolkit. First install the Visual Studio, then the NVIDIA toolkit. And after that, if you will go to the Visual Studio, create a new project. In new project, you will find out the NVIDIA CUDA. Generally, in Visual Studio will have the option for C, C++, and some other programming languages. The built-in compiler is available over there with the Visual Studio. You can add the CUDA compiler over there as well. So just use the NVIDIA CUDA. And when you will use the NVIDIA CUDA, what you will see, you will find a default program over there. You will find a default program will be there. When you will open a CUDA program, so by default, this simple vector addition program will be there. Vector addition program will be there, and just run this vector addition program. And if this vector addition program is running successfully, it means you have installed the CUDA properly in your machine and it is working fine. And now in place of that CUDA program, you start writing your program, and all the files, CUDA files will be saved at the extension with .cu. Okay, like that will be the .cpp by default in Visual Studio. You can save it as a dot. You have to save it .cu. Okay, so with the help of these softwares, you can set up the visual. You can set up the environment in your machine. If your machine is having a graphics card, NVIDIA graphics card, which support the CUDA programming environment. Okay, first you have to check that if it is having, install the Visual Studio, download the latest CUDA toolkit, and start your CUDA programming in a laptop and a desktop, wherever you want to be. Okay, so that's all from my side. Okay, that's all. So you can do the CUDA programming in any if you want to perform this in a Linux environment or a Unix, any Unix flavor, you can do it over there. So the CUDA toolkit is available for the Unix, all the Unix flavors as well. Just download it and install it, and use the command line to execute your program. You just need to check how to do that. NVCC compiler is used to execute your program. Okay, so that's all for hands-on side. Okay, Abba, you there? Hello, Pragati ma'am, you there?
Yes, sir.
Okay, that's all from my side.
Thank you, sir.
Thank you all. I hope you guys learn something. Just, it's really very easy programming language. Just start using it. You can easily do it. Okay, that's all. Thank you all.
Okay, thank you, sir. Thank you for the wonderful session. It was really enlightening, sir. And so the hands-on session had a good amount of practical application concepts using the CUDA programs, which encompassed ample amount of parallel computing concepts using the GPU, sir. And so on behalf of the participants, sir, I would like to extend my sincere gratitude for being a part of the workshop, sir. Thank you so much, sir.
Okay. Thank you all. Okay, I'm disconnecting from the meeting now. Okay, thank you, Pragati ma'am. Thank you all.
Thank you, sir. Again, thank you.